So today we're going to continue our discussion of basic properties of curved manifolds. And in particular, we're going to talk about how you define a derivative. And one of the reasons why we want to get into that is because if you have a general coordinate system, which is curvilinear so that it is not flat, then the problem is to define a derivative which has physical sense. If you're given, say, a vector in this direction, right? A vector that you would assume does not vary, so therefore whose derivative is close to zero, would look like something like that, right? And but you can see that the components at different positions are quite different because of the fact that the coordinate system is curvilinear. So in order to define something like a derivative of some vector v mu, we have to be careful because this object, as we write it down in this way, is not a tensor. So we'll have to do some work, and of course you can understand that derivatives are essential in trying to construct any sort of equation for general relativity. I mean, we did write down the equation for free fall. That was manifestly covariant, but we also need the field equation. So that means we have to be able to write down a derivative of the metric which will enter eventually the Einstein field equations. And in order to do that, we have to define a meaning, or the meaning of a derivative that makes sense. So let's consider a vector which is v prime mu. Now, if this vector is contravariant, then its change is given by dx prime mu times dx nu times v nu, right? And so what we want to construct is now the derivative of this thing. And so we're going to write down the derivative of v prime mu, right, with respect to dx prime nu. So prime upstairs and downstairs. And so this means that, well, we're just going to take this expression, right, and plug it in there, right? So as a result, we have the derivative of a product because you have to take the derivative of this and the derivative of that. So we get two terms. So the first term is just the dx prime mu, as we have there, times the dx nu, right, times the derivative of x rho with respect. So now we want to write the derivative with respect to x prime as a derivative with respect to x. So we write it as dx rho by dx prime lambda times dv nu, right, and then times dx rho. Right, and so with this index, sorry, we want to have this to be lambda. So that's one term, and then the second term is going to be the derivative of this prefactor, right? And so the derivative of the prefactor is now a second derivative of x prime mu, right? And now with respect to x nu and x rho, times the derivative of x lambda with respect to x rho to some other index, which we're going to call, say, we're going to call this lambda, and this is going to be a rho instead, and then times v nu. Right, so that's the second derivative of this term here. And so this would be the part if the derivative was a tensor, right? So if the derivative of v with respect to x was a tensor, then you would get these two factors of dx by dx prime or dx prime by dx. But this part here spoils the transformation property because you get an extra term which is not characteristic of the transformation properties of a tensor because it contains second derivatives. Right, and
yes, lambda prime.
Lambda prime, thank you. So what we can do now is we can look at the transformation properties. So look at the transformation properties of gamma lambda mu nu, right? And in particular, we look at how gamma prime mu lambda k v prime k transforms. So we look at an object which is similar to what we have here, except we don't multiply by the derivative, but we multiply by the affine connection, and we have primes on both sides. Now, this is something that we kind of worked out, some of it. And this is, when you do the algebra, this is dx prime by d mu times dx nu times dx rho by dx prime lambda times gamma nu rho sigma times v sigma. And so that would be the piece that, again, would make it transform like a tensor, right? Because you would have two factors that are either dx prime by dx or dx by dx prime, mu, nu, and so forth. But then there is a second term. But the second term has the following structure: the second derivative of x prime mu times dx rho dx sigma, and then times dx rho by dx prime lambda, and then times v sigma. And so that's again the part that makes this combination not transform like a tensor, right? But the important thing is that this piece here is actually the same piece that we have over on this side, except it comes with the opposite sign, right? So this suggests, right? This suggests that we should define a derivative by having this piece here and then add on the gamma part, right? So it suggests that we should defining a derivative in the following form. That is, we should first take the derivative of v mu with respect to x lambda, like we have done on that side, right? And then add on to it a piece where we have gamma mu and then lambda k and then times vk, right? And if we look at this object, so when we combine together the ordinary derivative and a piece that contains the affine connection, then the transformation law of this piece here gives us this second derivative term. The transformation law of the second piece also gives a second derivative term with the opposite sign. And so the combination of the two should transform with a prefactor, which is just a combination of these two, the dx prime by dx and dx by dx prime, which is what we have both there and we have also here, right? And so this is the definition of a derivative of v mu, and it is denoted by the semicolon symbol, right? So, and is called the covariant derivative. Covariant derivative. It's called a covariant derivative because now it is covariant in the sense that it is a genuine tensor, right? It is a two-index tensor which transforms in the appropriate way, right? And so now that sometimes is denoted, I think in the old days it was always written as a semicolon. By the way, if you use a comma, then it's just the ordinary derivative. So in some books you will find that mu comma lambda is just dv mu by dx lambda. Right. So that is why here the semicolon is used, because when you have the semicolon, then it's a covariant derivative, which means you add on the gamma term, right? And perhaps slightly more modern notation is to use the symbol and write this as gamma lambda v mu, right? And then this would be the derivative, the ordinary derivative of v mu plus the affine connection term, which is gamma mu lambda k times vk. So you'll find this often in the literature written as kind of a gradient or nabla symbol, this denoting the ordinary derivative, and that is the covariant derivative. Right? So anyhow, we like sometimes to write things in terms, explicitly in terms of derivatives that we do, because that way we can tell whether it's derivative with respect to x or some other parameter. It could be x prime or it could be psi. So we can define this covariant derivative also for a vector that is covariant, right? And so now you go through the same exercise, and the piece you pick up when you do the transformation of the ordinary derivative has the opposite sign. So now you have that for a covariant vector, right? For a covariant vector, you define v mu semicolon lambda to be the ordinary derivative, so dv mu by dx lambda. And now in this case, you have to subtract out the affine connection term, which is minus gamma k mu lambda times vk. So if you have a mu lambda. So if you have a covariant vector, then you have to have this opposite sign. Otherwise, it's the same story, right? So again, this object is a tensor, which means that if it is 0 in one coordinate system, then it will be 0 in all coordinate systems, which is not true of the ordinary derivative, right? Now, if you construct something that is more complicated, in the sense that if you have t mu nu and do a semicolon with respect to two indices, right, then the resulting expression is more complicated. In other words, there's going to be lots more terms with the gamma. You only have one gamma when you take the derivative of a tensor, of a vector, but if you have a tensor that has many indices, then there's going to be more contributions. And, well, we won't go into that, but you can find the formulas in the book. So, now, one interesting result that is very much relevant for the theory of relativity and the Einstein field equations is the fact that if you take the metric, right, so apply this to the metric, right, itself, right, because we're interested in figuring out what these derivatives of the metric look like, then so we can calculate the covariant derivative with respect to the index lambda, right? So this will be, again, following what we have written over there, and again, this is one example where you actually have two gamma terms because this is a two-index object. But this is equal to the derivative of g mu nu with respect to x lambda, and then minus gamma rho times lambda mu times g rho nu, and then a second gamma term, which is minus gamma rho. We're basically interchange the mu and the nu, and so minus gamma lambda nu times g rho mu. This is the definition of the covariant derivative of the metric, in the sense that it is only this combination of ordinary derivatives and affine connection which makes sure that this thing is a tensor. Right? So this is a tensor, which means that it transforms in the usual way. Right? It transforms, because it is a covariant tensor, it transforms by factors, which are dx by dx prime. Right? Now, we calculated something like this some time ago, 2 or 3 lectures ago. We actually calculated this combination, and we found out that this is in fact 0. This is 0, right? It's identically 0, and so that means that g mu nu semicolon lambda is identically equal to 0, which is interesting or disappointing depending on your point of view, right? So in other words, you don't get anywhere if you calculate just a derivative the right way, which means making it a covariant derivative when you apply that to the metric, right? And we can see that this is something that we can also obtain, if you want, from the principle of equivalence, or the principle of general covariance, because we expect a result like this, right? Because we know, first of all, that this derivative defined in this way is a tensor, right? So it will be 0 in all coordinate systems. But we do know that in a special coordinate system, which is the freely falling one, right? In that coordinate system, the metric is in fact a constant, right? And the affine connection is 0 in that freely falling coordinate system. And the ordinary derivative is 0 because it's a constant. The derivative of a constant is 0. So it has to be 0 in a freely falling coordinate system. It is also a tensor, which means it has to be then 0 in every coordinate system, right? So this result is in fact not unexpected, right? So this is a tensor, and it is equal to 0 for G mu nu becoming the flat metric at the flat metric eta alpha beta, right? So that is, of course, a little bit of a roadblock, as I already think I mentioned in the last lecture. It's a roadblock because you want to construct some sort of field equations which has the derivative of the metric, and you find that the derivative of the metric is 0. Right? So how are you going to write a field equation? Right? So it means that you have to do quite a bit more work. Right? So now we are going to pursue the mathematics of this a little bit more, so that we can collect a number of results which are useful later on and not have them to derive as we go along. So there is another useful and interesting consequence of this fact that the covariant derivative of the metric is always 0, and that is that raising and lowering indices commutes with a covariant derivative. So taking covariant derivative commutes with raising, lowering indices. Well, that is, of course, very useful because you suppose you take a vector, which we indicate by v nu, and you multiply that by g mu nu, right? The metric g mu nu, like this, right? And now you want to take the covariant derivative of this with respect to some other index, lambda, right? And now you don't have to worry about taking the derivative of this thing, right? Because in fact this is just equal because the derivative, the covariant derivative of the metric is 0. This is just simply the same as doing g mu nu times the derivative of v nu with respect to lambda, right? So the operation of covariant differentiation and raising and lowering indices commutes. So this suggests the following recipe to construct equations which are generally covariant. So recipe for equations in general relativity, right? And the first thing is to write equations which are valid. Equations which are valid in freely falling coordinate systems, or if you want, in inertial system or special relativity. Right? So if you have an inertial coordinate system, then the equation should be valid. And the second thing that you require is that the equations be generally covariant. And so you are going to take the metric eta alpha beta, and you're going to promote that to a g mu nu, which in general depends on x, which is of course not the case for the eta, right? And so the third aspect of this recipe is coming from what we discussed today. And so the derivatives here are going to be replaced by this semicolon symbol right? Or what we referred before as also d mu, right? So in other words, if you want to have equations which are going to be valid in the presence of gravity, then you have to add this gamma term, and you replace all derivatives by covariant derivatives, right? And so this is actually similar to electromagnetism, right? There is a similarity in electromagnetism because one of the things that we discover when we do electromagnetism, electromagnetic interaction in the quantum mechanics of electromagnetism, or interactions that do involve electromagnetism, like in the Schrödinger equation, is that in fact the replacement, right, so-called minimal substitution, right, where we do this replacement where p mu is replaced by p mu minus E over C A mu, right? For example, if you have a particle in a magnetic field, that is what you do, right? Remember that the Hamiltonian for a particle in a magnetic field is 1 over 2m, the non-relativistic one, P minus E over C times A squared, right? Where the curl of A is equal to your B field, right? So this is what we do in classical mechanics, and we also do it in quantum mechanics, right? Because in quantum mechanics, you actually replace P by h bar over I times the gradient, right? And that is how you get the Schrödinger equation, right? So, well, this corresponds, of course, again, when we talk about the P as being a derivative, this corresponds to the replacement of d mu goes into d mu minus IE over h bar C times A mu, right? And so this replacement that we do in electromagnetism is very much similar to the replacement that we are doing here, right? Because, right, this substitution is the one that, by the way, ensures gauge invariance. The substitution is the one that ensures that you have a Schrödinger equation which is still gauge invariant, right? And so here in GR, we have something that is very similar because we replace the ordinary derivative by this covariant derivative, which is the ordinary derivative plus or minus the gamma term, right, which has indices to it, right? And the sign depends on whether you're talking about a covariant or contravariant vector or something maybe even more complicated. So there is an analogy, therefore, between the gamma lambda mu nu and the A mu field. Right, the correspondence is that the gamma is playing a role which is similar to the electromagnetic field, which is kind of interesting because you might have thought that, of course, the analog of the electromagnetic field was the metric G mu nu. But if you do look at the way the derivatives are constructed, then it is in fact the affine connection that is the analog of the electromagnetic field, right? So, of course, this is a very deep correspondence. It has to do with the fact that both gravity and electromagnetism are gauge theories, right? So there is a gauge particle that is associated with this local invariance, right? The gauge particle is the photon. In the case of electromagnetism, it is something else. It's the graviton in the case of general relativity, right? So, now, let's continue a little bit on the mathematics of this, and let's see what else we can extract from the kind of properties that we have written down for derivatives. So, more properties. Properties of derivatives. More properties of derivatives, and which again will be useful later on. And so one of the things that we're interested in is if we take a vector, right, and we now take the covariant derivative with respect to that, if we now sum over the index that we take the derivative of, then this is a covariant divergence. Covariant divergence because these two indices now are the same, right? And so this is equal, right? This is going to be equal to dv mu by dx mu. So now the two indices are the same. And so we also get two indices which are equal in the affine connection. So we get gamma mu, mu lambda, and then v lambda, right? Now, because of the two indices are the same, this simplifies, right? So you can look at the definition of the affine connection, and this is just equal to, this is equal, the gamma part itself, right? Is just equal to 1/2 g mu rho times one derivative of the g. So times derivative of g mu rho, or rho mu, with respect to x lambda. Right? So you notice that the two indices are in fact the same. And well, that can be simplified quite a bit more. And we will not go into that because it uses the fact that you can prove that if you take, so it can be written in terms of the determinant of the metric. Can be written in terms of this quantity g that we define to be minus the determinant of the g mu nu. The g mu nu regarded as a 4x4 matrix. And the result is based on the fact that the variation of the log of the determinant of g, of the metric g mu nu, is equal to the trace of the variation of g with respect to g itself, or the inverse. Right, so this thing here is just g to the -1, right, the inverse metric, right? And so you can do a few manipulations and you find out that that results in v mu semicolon mu. So the covariant divergence is the ordinary derivative. So it's the derivative of v mu with respect to x mu, ordinary derivative, and then summed over, which is the ordinary divergence. And then plus another term and you can combine those together. So let me do that here. You can combine it into a single term, which is 1 over the square root of the determinant of the metric times the derivative with respect to x mu of square root of g times v mu. So you can write in terms of something that is actually a little bit simpler than just taking covariant divergences, which normally involve the gamma symbol, but in this case you can do without it. Right? And so this is useful for the following reason, because we are going to have a number of conservation laws, and when you have a conservation law, then you want to look at whatever charge is conserved from that conservation laws. So useful for conservation laws. Right? Because suppose you have this divergence, v mu semicolon mu, so this covariant divergence of some 4 vector, right? And suppose you want to integrate this over all space. Well, integrating over all space means that you integrate it, right, using the volume element, which is dv. But the volume element is actually the integrand d4x times the square root of g. The square root of g is the square root of minus the determinant of g mu nu, right? And well, the reason why this result here is useful is because normally you would have trouble in writing this as a boundary term. You would have trouble in writing it as a term that can be written as something that depends on the fields at infinity. But that is not the case here, because this root g is kind enough to actually cancel out this term here, right? And so this can be written as just the integral in d4x, where the only remnant is d by dx mu of root g v mu. So d by dx mu of root g times v mu, right? And so there is no factor in here. So that means this is indeed the integral of a derivative, and so can be written as in a simpler form as a boundary term. If the fields vanish at infinity, then this is 0. Right? Or if you have a surface that doesn't have any boundaries. So this is a very useful result, and so something that we are going to rely on later on. Now, let's talk about something else, which is related to what we have just done, which is the covariant differentiation along a curve. So covariant differentiation along a curve. So we use what we learned up to now, but we're doing this covariant differentiation along some sort of curve. So that means that we have a curve, right, that goes from point A to point B, which is characterized by some coordinate, which is x mu of tau. And typically, there's going to be some quantity which is non-zero only on that curve, because the curve is associated with the path of a particle, right? So, for example, we can have the 4 momentum, right? And that is going to be proportional to some delta 4 of x mu minus x mu of tau. Right? So the 4 momentum associated with the particle is going to be 0 everywhere except where the particle is located, which is along that trajectory. Right? So that means that we can define the differentiation along the curve. So that is done in this way. So first of all, let me consider some 4 vector, and let's look at its transformation property. So we calculate a prime mu along that curve. Right? And so this is going to be, if this is indeed a 4 vector, that prime will tell us that we have to add dx prime mu by dx nu, right? And then times a nu of tau, right? Where this factor here is evaluated on the curve. So that means that x is equal to x of tau. The 4 vector x is along that curve, right? So the next thing we do is differentiate with respect to tau. So with respect to this parameter that describes how far along we are along this curve, right? So that means that we calculate dA prime mu by d tau, right? And again, we have 2 terms. So we have the derivative of x prime mu by dx nu, right, times dnu by d tau. So this is a term that we get by just differentiating this part here. And we also differentiate the first guy. So that means that we get the second derivative with respect to x prime mu of dx nu dx lambda, right, by dx lambda by d tau, and then times a nu. So in the second term, we've taken the derivative of this prefactor with respect to tau, but we have written the derivative with respect to tau as the derivative with respect to x lambda and then the x lambda by d tau, right? So this is again an affine connection term. Affine connection term. And so we can write so we define, therefore, right, the derivative along a path, along a curve, to be the ordinary derivative, right, the ordinary derivative, dA mu by d tau, right, plus an affine connection term, so plus gamma mu times nu lambda. And now times, we need all this factor here as well, and that is just the for velocity, right, of the particle. So we have a dx lambda by d tau, and then we have the vector a nu, of course, again, and define this to be the derivative along a path, right? So that is what is meant by this symbol, capital D. And this is a 4-vector. It's a 4-vector. So if we define the derivative of a 4-vector as just the ordinary derivative along a path with respect to parameter tau, then that fails again to be a covariant object, right? But if we add an affine connection term with the right indices, then that is a genuine 4-vector, right? And so this leads to the notion of parallel transport. Leads to the notion of parallel transport because a parallel transport is what you do to a vector when that derivative is 0. Right? So parallel transport is what you have when you consider a path, right, like we had before, and you define that on that path the vector a mu does not change in the frame attached to the particle, right? Which is supposed to be a locally inertial frame. Right, so you have a frame that is attached to the particle, and that is a freely falling frame psi alpha. Right, so you can visualize that frame as something that looks like that. Right, so in that freely falling frame, so that is denoted by psi alpha, which depends on x of tau, right, because it is attached to the path of the particle. And in that frame, you have two things. The first one is that gamma is 0 because it is a freely falling frame, right? So the affine connection is equal to 0. And the second thing that happens in that frame is that because that in that frame you have that dA mu by d tau is equal to 0 if vector a mu does not change. Not change in direction. So if you have a vector that is attached to the particle and that vector does not change direction as the particle is freely falling, right, then in that frame the derivative is 0, right? And because the equation for parallel transport along a path is written in terms of vectors and is a tensor, that implies that in fact dA mu by d tau is equal to 0 in any frame. Right. So in fact, if the 4 vector that is attached to the particle does not change direction in the freely falling frame, then you have that this is equal to 0, or this is the equation that is satisfied by it. Right? So this is the equation that dA mu by d tau is equal to 0. Right? So the equation of parallel transport says that the covariant derivative of a vector that does not change direction in the freely falling frame is 0. And as a result of that, the ordinary derivative is equal to minus the affine connection term as viewed from any frame, not just the one that is attached to the particle. Now, in fact, the geodesic equation is precisely an equation of this type. So if we look at the geodesic equation, it is of this type. It is an equation of this type because you can write it as now you do remember that the equation for geodesics is that the second derivative of x mu with respect to tau, right, plus gamma mu lambda sigma dx lambda dx sigma by d tau is equal to 0. So it has, in fact, some of the ingredients of the kind of things we talked about up to this point. It has derivative with respect to a parameter, which is the proper time, and it contains the affine connection. And in fact, this is nothing but, can be rephrased in terms of what we just defined, namely as a derivative with respect to d tau. This should be a capital, by the way. Yeah. Better to write it as a capital. D by d tau of dx mu by d tau is equal to 0. Because if you write it in this way, you get the ordinary derivative, which is the second derivative with respect to tau squared, and then the affine connection term, which is exactly this one. Because you see you have the 4 velocity here. Right, this is the 4 velocity term. This is u lambda equal to 4 velocity. So what does that mean? It means that, well, the geodesic equation is the equation of parallel transport. It's equivalent to it, and which means that the geodesic is the shortest path between 2 points, right? That we learned a week ago, right? Because the variation of a proper time was 0. And it's the shortest path, but it's also the straightest path. Straightest path between 2 points. So the geodesic corresponds to a line where the velocity, the 4 velocity, is not rotating in the frame that is attached with the particle. So for a freely falling particle, the 4 velocity, u mu, which is defined as dx mu by d tau, is parallel transported along the path. So that means that the 4 velocity is always tangential to the particle's trajectory. right? So it has this property that in the frame attached to the particle, the forward velocity is always like this. It has this property, right? So as a result, the geodesic is the straightest path, not only the shortest, but the straightest, because the velocity is always going in the direction of the motion, right? And so let's look at an illustration of parallel transport. Where we have, so let me delete that. And so let me look at a sphere. And in fact, it will be easiest to just visualize what happens on Earth when you do this kind of parallel transport. So here you have north and south, right? And so let's visualize what this equation of parallel transport means. Right? What does it mean to have this covariant derivative along a path to be 0? So let's start here at a point, and let me take that vector, right? That vector that we denote by A there, right? So that's my A vector, right? Let me take it to a point in some direction, right? And so let me now parallel transport that vector along a path. And parallel transport means that the vector is always kept parallel to itself, right? Just like the velocity is always following the path. In this case, the parallel transport is going to be done along this path here. So we're going to go from that point to this point. And when you parallel transport, say, along the equator, you're going to end up with a vector that will still point towards the North Pole, right? So you walk around like this. And now when we get to that point, we are going to parallel transport this vector to the North Pole, right? So that means that we bring the vector up like this. And as we arrive at the North Pole, we are, of course, going to discover that the vector is going to point that way, right? By parallel transporting along this geodesic in this case, right? And so now we're going to bring it back to the point of origin. So we are going to do the last leg of this closed path. So in this case, we're going around a circle. And what we do discover is that after we've done this parallel transport, we are going to end up here with a vector that does not point along the original direction because it is like that, right? So it is characteristic of curved surfaces that when you do this parallel transport, you end up with a vector that is pointing in a different direction, right? And so here is another example of a vector that is parallel transported along a closed path, right? So I have a vector here, and as I move along this path, I'm making sure that the vector always is pointing in the same direction as I go around this thing, right? And of course, by the time you get back to the original point, the vector will be pointing the same way if the manifold is flat. But things do get interesting if the manifold is not flat, which we can arrange in this case by just having this object turn into a cone, right? Because in this case, now you do have that the manifold is no longer flat. There is curvature, which is localized at the vertex of the cone. And you can see immediately that as soon as you do have curvature, in fact, when you parallel transport the vector on this closed path, it does not come back to itself. Does not come back to itself. There is an angle between the original vector and the parallel transported one, and that angle is in fact directly related to the curvature that is in this case localized at the vertex, because for this particular manifold, in fact, the manifold is flat everywhere except at the vertex. So this notion of parallel transport is very important and crucial in discussing properties of general relativity. So if we look at an equation like this, right? So if we look at the equation for parallel transport, which involves this forward velocity, then this can be regarded as an ordinary differential equation, right? which tells us how the vector is going to change as we go along this path, right? And so in principle, we can integrate it to find a mu as a function of x of tau. Right. So we can integrate this equation. And so that will give us the evolution of this 4 vector, right, as we move along this path. Right. And so in principle, we can write integrating equation of parallel we can integrate this equation, and let me look at one example which is not the 4 velocity, but which is one where we have a mu that becomes the spin, right? So an object that is a little bit different from anything that we considered so far. We talked a little bit about the spin in special relativity, right? Again, the spin is something that is associated with a particle that is moving along a certain path, right? So we can have this spin S mu. Remember, it can be promoted to a 4 vector, right? And so it looks like an interesting physical object to look at. Now, the spin, if I write the index downstairs, then there would be a change of sign here, right? So the equation, because remember, every time you switch from covariant to contravariant, and the covariant derivative has a different sign for the gamma term. And so the equation here is going to be ds mu by d tau is equal to gamma lambda mu nu times the velocity term, so times dx nu by d tau, times the spin part, so times s lambda. Right? So this is the equation for parallel transport, which says that ds mu by d tau is equal to 0. Right? In other words, the spin does not rotate in an inertial frame that is attached to the particle, right? Because there's supposed to be no forces acting on the spin except gravitational ones, right? And the gravitational forces are in here, right? So this is where the gravitational forces. Gravitational forces are hidden in that gamma, right? And so we can multiply both sides by d tau, right? So we can write this as ds is equal to gamma times dx times s itself with suitable indices, right? So you see the d tau appears on both sides, so we can, if you want, you can get rid of this, right? So the rotated vector s prime is going to be s plus ds, right? And so is going to be equal to 1 plus gamma dotted into dx times s itself, right? And so that's for an infinitesimal displacement, right? And so we can formally integrate that equation by writing it in terms of a rotation matrix. Right? And so we can write it in terms of a rotation matrix. Right? And so that rotation matrix is going to be called R. And so we can write S prime with index up, S prime mu, is equal to R mu nu times S nu, right? And so for a finite rotation, this is given by a rather complicated expression because r mu nu is given by the path order product of e to the minus an integral around a loop. So we consider a closed loop. So in other words, instead of taking a path which is from A to B, we're going to consider a loop, right? And so we can write this as a path ordered product along this path C of dx prime lambda times gamma lambda with some indices, right? And so that's going to be a matrix, and we have to write the exponential of a matrix, which is something that we learned, for example, in quantum mechanics. And then we're going to get another matrix back from the exponential, which has two indices, mu nu, and that is going to go in there. So in principle, you can write what this rotation is going to look like, even when you have a finite rotation and not an infinitesimal one. But the expression is going to be rather complicated because, in general, what appears in the exponents are matrices, and the matrices don't commute, so you have to have this infinitesimal rotation along the path, taking into account the path ordering. So anyhow, so parallel transports. Can be used to detect curvature. Can be used to detect curvature. Because it is clear that if you are in flat space, then of course the gamma is 0, right? And if the gamma is 0, then this is the identity matrix. And the equation for parallel transport that we have here, that part is 0. So the derivative is 0. And so if you have some non-trivial rotation, then it means that there is some curvature in the manifold, right? And so this example, right, with the paper shows how that comes about. So let me spend a little bit of time in discussing where we are at this point, and in particular the analogy with electromagnetism. So pursue analogy with electromagnetism a bit more. Right? Because what we have learned so far is indicating that there are some interesting correspondences, right? So let me look in electromagnetism at local gauge invariance. Right? And so this is something that we learned, for example, in the quantum mechanics class, right? And so we have, of course, the electromagnetic field, mu of x, right? And we have also matter fields, right? So matter fields are described by some psi of x, for example. Right? And so the kind of setup we would be thinking about would be, for example, the Schrödinger equation, right? Or the Dirac equation, right? And so the equations for a particle that is coupled to an electromagnetic term are preserved. So equations are preserved if we do the following. Well, first of all, we transform the electromagnetic field by A alpha goes into A alpha plus a gauge piece, right, plus d by dx alpha theta of x, right? And let's write here x everywhere, right? So we know, for example, that Maxwell's equation is already invariant under this transformation, where this is some sort of gauge function. Right? So we know Maxwell's equations are invariant under that, and that the Schrödinger equation or the Dirac equation is invariant under psi of x getting multiplied by a phase. So getting multiplied by e to the I e times theta of x times psi of x. If you do this transformation simultaneously on the electromagnetic field and on the matter field, you get the equations are invariant, right? And a useful ingredient in showing that you actually have this invariant, a useful ingredient in proving that the equations for that the equation for a particle in a magnetic field, for example, if you look at the Schrödinger equation, a useful ingredient is to introduce this gauge invariant derivative. Gauge invariant derivative, which is done in the following way. You take d alpha, so you use the capital symbol, right? And you apply that on psi of x, right? And this is defined as taking the ordinary derivative, d by dx alpha, and adding to it the minus IE A alpha of x that I had a moment ago, and multiplying that by psi of x. Right? And so this is the analog of this covariant derivative that we discussed for the gravitational field. And the important property that this derivative has is that it transforms like the field itself. Namely that d alpha of psi under a gauge transformation, right? So we're going to do this combined transformation of the A field and the psi field. The A field gets shifted by a derivative of theta, right? Because that's coming from this derivative term. But at the same time, the field acquires a phase, and so that phase, this derivative gives a phase term, and the gauge transform of A also gives a theta term, and the two terms cancel out. And so this just turns into e to the I theta, e to the I e theta of x, times the same derivative, d alpha, acting on psi. So that means that d alpha of psi transforms like psi itself. Transforms like psi itself, right? So that means that if you want to construct, for example, a Lagrangian density for a field psi, then what you would do is you would take d mu minus IE A mu, right? And you would have that act on the field phi, and then you would take, say, if the field is complex, you would take the square of that. And this would be guaranteed to be gauge invariant. And this is, in fact, exactly, right, the Lagrangian for the Higgs field, right, up to potential terms, right? So when you have a scalar field, you want to couple in this way. And in the Dirac field, the same story applies. So if you have the Dirac equation of the Dirac field, then you will still use d mu minus IE A mu, right? And in that case, you will multiply it by a gamma matrix, right? And then you will have a psi and a psi bar, right? So it is always this combination that ensures that you have something that is gauge invariant. So this recipe that works so well in electromagnetism and that ensures that you have gauge invariance everywhere. Right? This principle of gauge invariance that allows us to write down things which have this invariance property is there also in general relativity. Right? In general relativity, you also have this general covariance that requires you to write derivatives in terms of the affine connection. And if you do introduce the affine connection, then everything is going to be well behaved, and you will be able to write down equations which are form invariant when you go from one coordinate system to another. So the analogy with electromagnetism is quite useful and appropriate. And so this suggests, right, it says gauge invariance in the Schrödinger equation, in the Dirac equation, and in QAD, right? That suggests that in gravity we're having the same thing, right? And that this replacement here that we do here is similar. So in gravity, it is the replacement of derivatives, right, by derivatives plus or minus this gamma term, right? So this gamma term is playing the role of the electromagnetic field, right? So that is the thing that needs to be added so that the equations are invariant, right? Now, in electromagnetism, we have one more consequence of this gauge invariance, right? And the consequence is that the electromagnetic current is conserved. All right, so local gauge invariance. Local gauge invariance leads to a conserved electromagnetic current, right? And so again, if you're dealing with a Schrödinger equation, the electromagnetic current, right, is something that looks like this. J alpha of x is equal to minus IE, and then we have a combination of derivatives of the field. So it would be psi dagger if the field has more than one component, otherwise it's just psi star, times the derivative d alpha, which is the one we defined here, right? And then times psi minus psi times d alpha psi dagger. Actually, it's the dagger of the whole thing. So this expression here. And you can now calculate d by dx alpha. I'll leave that as an exercise to calculate this object. Right. And this is identically 0. Identically 0. So whenever you have a local invariance, then you have a conserved current. In the case of electromagnetism, the local invariance has to do with this parameter theta of x, and the conserved current is the electromagnetic current, J alpha of x. Right? And it is locally conserved. Locally. So at every point in space-time, there is this current conservation constraint that whatever, if the charge density changes at some point, then there has to be a current that flows in or out of that region. And furthermore, the equations of electromagnetism, that is Maxwell's equations, are inconsistent unless we have that relationship, unless d by dx alpha j alpha is equal to 0. Maxwell's equations are inconsistent. So you discover that already when you have your first course on electromagnetism. When you look at Maxwell's equation, you know that if the continuity equation is satisfied, then Maxwell's equations are consistent. Otherwise, they're not. Right? So there is a number there is a sequence of relationships between these different statements having to do with local gauge invariant current conservation and the consistency of the field equations for electromagnetism, which are all tied together. In fact, the statement that local gauge invariance implies the conserved current is one application of what is called as Noether's theorem. Noether's theorem. So Emmy Noether, around 1922, I believe, she was a mathematician working with Herbert. And so she proved this theorem, which says every time you have a symmetry, every time there is some sort of symmetry, then there has to be a conservation law. Right? So in electromagnetism, that symmetry is local gauge invariance, invariance under these phase transformations, right? And there has to be a quantity that is associated with that symmetry, which is conserved, and that's the electromagnetic current. So all these things go hand in hand and tie up together. And so what is the relevance of this for general relativity? Well, for general relativity, of course, in many ways, we have seen that things are working the same way, right? That you have this affine connection that is playing the role of the electromagnetic field. And so you can establish a correspondence with some of the other items that we have over there. First of all, we can ask, what is the invariance? Well, of course, the invariance that in electromagnetism is just a simple phase transformation. In gravity, it is the invariance under general coordinate transformation. It's a much bigger symmetry group, right? So the fact that you can change coordinate systems locally at every point in space-time is the analog of this very simple phase transformation that you have in electromagnetism, right? And Noether's theorem applies as well, right? Because it says because there is this big invariance, there has to be a set of quantities which are conserved. And so what are the quantities that are conserved in general relativity? Well, it is not going to be anything as simple as this. It's not going to be the charge. It will be the analog of the charge in general relativity or in gravity. And what is that? Well, of course, that is the energy momentum tensor, right? The energy momentum tensor is going to satisfy, already it does satisfy, as we saw in special relativity, an equation of this type, right, where we have d by dx alpha, t alpha beta is equal to 0 in gravity, right? Or special relativity, I should say, because we haven't gotten to the gravity part yet, right? So in special relativity, we had that this tensor was conserved. And as a result of that, the naught component, which is the total energy and momentum, are also constant, just like the charge is conserved here, right? That implies, this equation here implies that Q is equal to constant, right? Its time derivative is 0. And so here we have that the T naught alpha, right, are also conserved when they're integrated over some region, right? So the Q, which is the integral of the J naught, is conserved, and here it's the integral of the T naught alpha, which is conserved. So you still have the same kind of things repeating again, that you have a symmetry, and as a result of the symmetry, you have a conservation law. The conservation law has to do with energy and momentum, which leads us, in fact, to the last aspect, which I discussed. And the last aspect is what we have at the bottom, namely that in electromagnetism, Maxwell's equations are inconsistent unless the electromagnetic current is conserved. And so there is an analog. There will be an analog of that as well in gravity, which is that the field equations for gravity cannot be consistent unless energy and momentum are locally conserved, right? So that is one of the things that is going to come out, is that you have to have a conservation of energy and momentum at each point in space-time, because that is what is coming out of the local symmetry. So you can draw, if you want, a table, right, where you have things that are relevant for electromagnetism on the one side, and you have things that are relevant for gravity on the other one, and you can just draw correspondences, right? And the correspondence works pretty well, as I illustrated here in many aspects. Not all of them, right? Where is it that it doesn't quite work that well, right? Certainly there is a symmetry, and the number of conserved quantities works out well in both theories, right? But where does the symmetry, the correspondence between electromagnetism and gravity, where does this apparently, to some extent, kind of break down? It breaks down because in electromagnetism you just have the a mu field, right? And the quantity that corresponds to it in gravity is not the metric, it's the gamma, right? So the correspondence appears to be that the a mu is like this gamma lambda, right? And so because the covariant derivative involves the gamma, right? And in electromagnetism, the a mu is the primary field, right? It's the fundamental field, right? So if you know the a mu, then you know everything there is to know, and you can calculate the electric and magnetic fields from it. In gravity, it's a little bit different because this gamma lambda is not a fundamental field. It's not a fundamental field because it's the metric that is the fundamental field. So by taking then derivatives of the metric, you get the gamma, right? You get the gamma out of that. Right? Now, there's going to be a further element in this because, of course, in electromagnetism, you have the field strength tensor, which is the F mu nu. And, well, there is an analog in that of gravity, and that is the Ricci tensor. Right? So there's going to be, or the Riemann tensor, if you wish. So you do have a further correspondence to which we have not come yet, and to which will come in a little bit. And that is the analog. The electric and magnetic fields in gravity are the curvature tensor, right? And so that part is clear. That correspondence part is clear. In fact, what we will learn as well is that we learned to some extent so far yet. What did we know about the a mu, that you can gauge transform it, and we also know that this object, in fact, is not a tensor. Right? We know, just like this is not invariant, this one is not invariant either, right? Because this is not a genuine tensor, the gamma, right? So it depends on the coordinate system. But we know that the E and B fields are in fact gauge invariant, right? And that's going to be true also of the Ricci and curvature tensor in general, that they do not depend on the coordinate system. That if you're 0 and 1, then they're 0 in all coordinate systems, right? So anyhow, this is a deep analogy, and ultimately it has to do with the fact that both of these theories are gauge theories. Both gravity and electromagnetism are gauge theories, and both have an exact invariance, and that invariance you will only have if the particle is massless, because we do know also that in electromagnetism, if you add a mass to the photon, you break that invariance. So it is essential that that mass term is not there, and this is true in gravity too. In gravity, you cannot have a mass term. The graviton cannot have a mass term. Gravitational waves have to travel at the speed of light in vacuum. Otherwise, you break general covariance. And so that is as another thing that comes out of these considerations, which is very important, and is something that we have to deal with and live with and understand that these constraints are there. And if somebody someday finds that the mass of the photon is finite, well, we should be concerned, because that would mean that the current conservation is no longer there, right? So anyhow, we'll continue on this. In the next lecture, we're going to come back from the mathematics back into a little bit more physics. That is, we're going to try to understand how you write down equations for the gravitational field, which are generally covariant, using all these nice forms for derivatives and things that we learned today. So,
what's the analogy of the metric field in electromagnetism?
There is no such thing. There is no such thing. The analog would be something that some field that you write down, right? Presumably maybe some sort of scalar that you would take then a derivative, and out of that derivative you would get the a mu field of electromagnetism. And such a thing does not exist, right? The a mu field of electromagnetism is the fundamental field. Many of these considerations actually go way beyond electromagnetism, because we have learned now that the weak interactions are described also by a gauge theory, which has these W's and Z's. And we have learned that the strong interactions are described by gauge theory, which is called quantum chromodynamics, where you have an octet of polar gluons. And you have also there an exact local invariance, and you have a conserved color current. So it looks like nature, for whatever reason, likes gauge theories. And one of the things that I think is important and relevant to point out in this class is that all 4 fundamental forces in nature are described by gauge theory, and they are therefore associated with the exchange of a massless particle. Because if you didn't have a massless particle, WZ, before they get a mass to the Higgs mechanism, the gluon is massless, the photon is massless, the graviton is massless. All of those particles are massless, and all 4 forces in nature are described by gauge theories. So, as I said, nature clearly likes gauge theories. It is important for this class to understand that from this point of view, gravity is not an oddball, that gravity falls into that general category, that it does have very much the same properties as the other forces in nature because of this local invariance and conservation laws and so forth. And that, of course, was very much Feynman's point of view in his lectures. He wanted to say, look, gravity looks like electromagnetism, except you have a spin 2 particle, not spin 1. And so you're going to have more indices, but in many ways it's very similar. So we'll come back to that, and of course that's a very important thing to keep in our mind, right? Because if gravity really looked very different, then we would wonder, why is it that one of the forces in nature is so much different than the other ones? And it is nice that that does not seem to be the case, that in fact it is very much similar to the other interactions that we encountered before if we construct this table of correspondence, with some exceptions, right? And, but that has to do with the fact that gravity is spin 2, so you have to have this more complicated structure because of that, with the metric and the affine connection being constructed out of derivatives and such. All right, so I'll see you on Thursday then.